Hello, my name is Fariba. I am going to share with you my final project of the Recurrent Neural Networks for Sequence Data course. This project consists of the following sections. Part 1, a time series dataset. I have collected a publicly available time series dataset and reported its critical information. Part 2, RNN, simple RNN with sine wave data. I have generated a sine wave dataset. Then I have built, trained, and evaluated a simple RNN. I will discuss this part in Python. Part 3, RNN, LSTM cells, core concepts. I will discuss the core concepts of the LSTM cell. I will also discuss similarities and differences between cell state in LSTM and hidden state in simple RNN. Part 4, RNN LSTM with time series data. I have collected a stock time series dataset. I have built, trained, and tested an LSTM neural network. I will also discuss this part in Python. Part 5, design the neural network. I have changed several parameters of the LSTM neural network and evaluated their performances. Part 6, compare network performance. I have compared the best and worst LSTM neural networks built in part 5 with the built network in part 4. Conclusion, I will cover what I have learned from this project. Part 1, a time series dataset. I have collected a time series dataset related to 2019 novel coronavirus. The name of the dataset is COVID-19 Master that contains the number of confirmed death and recovered cases all over the world. This time series dataset is being collected daily by the Johns Hopkins University Center for Systems, Science and Engineering. This dataset has been collected from this link provided here. Data collection has begun on January 22nd, 2020 and is constantly being updated. The dataset contains 254 records according to the regions. The dataset also contains the name of each region in text, its geographic coordinates, and its associated number of confirmed death and recovered cases, as can be seen in this figure. Part 2, simple RNN with sine wave data and keras. In this part, I have built, trained, and evaluated the model using the cross-sequential model. First, I imported the Python libraries. I have generated a simple sine wave data ranging from 0 to 64 with 1024 values. I have split the dataset into training and test, 80% as train and 20% as test. The index of the original data is from 0 to 1023, and the index of training data is from 0 to 818, and the index of the test data is from 819 to 1023. Then I normalize the values and scale them between 0 and 1, numerous time series. With 50 values have been generated to train the model. I have built a complete simple RNN consisting of 2 subnetworks as shown here. The first subnetwork is the simple RNN and the second subnetwork is the feed-forward neural network consisting of fully connected layers. A simple RNN has been generated using the sequential model in keras containing 100 neurons. Then a fully connected layer has been added for the final prediction containing only one neuron. Therefore, the designed model is trained based on the time series generated. Training the model requires model compiler, ADAM as an optimizer, and mean square error as the loss functions have been introduced. Then the model is fitted to the time series generated in 5 epochs. The loss function shows that the performance of the trained model is quite acceptable since the loss function is approaching 0 over time. Then the trained model predicted the first value in the test data set. The predicted value would be used as the last value of the time series. This process continues until all the values in the test data set are predicted. The predicted values are compared with the actual values in order to evaluate the performance of the trained model. As shown here, the predicted values in the orange color are quite close to the actual values on the blue curve. Therefore, the designed simple RNN seems accurate in prediction of these time series. Part 3, RNN, LSTM cells, core concepts. Question 31. Discuss the cell state and of the LSTM cell. An LSTM cell has a cell state in addition to hidden state as the memory. The cell state addresses long-term memory, whereas hidden state only addresses the short-term memory. There are 2 different ways to look at the cell state. The first view is termed as flow in a channel. The cell state represents an information transporting channel in which the information can move freely from the start to the end of the sequence and not being reduced by anything throughout the channel. Because no weight is involved in the cell state, any later time step can use information carried in from the previous cell state without any reduction. The second view of the cell state is a snapshot of the state of a cell that represent what happens at some time steps along the flow. In this view, the cell state represents the available information that can be memorized at this state, no matter how early the information is in the sequence. This implies how cell state in the LSTM can address the vanishing gradient problem of the short-term memory that exists in the simple RNN. Question 3.2. Discuss the gates of the LSTM cell. The role of gates is to manage the information along the sequence chain. In fact, information can be added or removed to the flow via gates. Gates have 2 purposes. The first one is filtering out the information that is not allowed to get in or get out, and the second one is controlling the flow of information. An LSTM cell contains a cell state and 3 different gates, including forget, input, and output. The forget gate. The inputs of the forget gate is the previous hidden state and the current input that gets into the cell. The forget gate decides which information of the previous cell state, CT-1, should be kept or which one should be forgotten. These decisions are technically made after reviewing the inputs. The output vector layer of the forget gate is called remember vector, FT, that contains values between 0 and 1. Therefore, the remember vector is used to update the previous cell state, CT-1. The forget gate learns how to review the inputs to make these decisions as skills during the training process. The input gate has 2 activation functions, sigmoids and tanh. The same inputs are entered into the input gate as well. The input gate also reviews the inputs to decide which information from the input is useful and should be added into the current cell state at time step t. The filtered inputs by the sigmoid function is called IT. Next, the input gate modulates the inputs into the values between -1 and 1 by using the tanh activation function and produces a ctemp. Then IT and the ctemp are multiplied to obtain the final output of the input gate. The final output is the useful information from the inputs that will become part of the new cell state at the time step t and is called save vector. The save vector will be added to the current cell state and make the new cell state. Therefore, the information kept from the previous cell using the forget gate and the information added from the input gate construct the new current cell state and becomes as an input to the output gate. The output gate modulates the new current cell state by tanh activation function and produces the tanh CT. The output gate also reviews the inputs by sigmoid function to decide what information from the inputs are relevant and produces OT. Next, the modulated new current cell state is multiplied by OT to produce the hidden state at time t. Therefore, the output called focus vector represents the current hidden state HT of the cell at time step t. Overall speaking, the output gate decides what information from the inputs and the new current cell state CT should be used to make the new current hidden state HT at the time step t. It is worth noting that each gate is a neural network and can mitigate the human's brain system. Each gate can learn due to their sigmoid activation function that has values between 0 and 1. Data is being kept by multiplying any number by 1, whereas it is being forgotten by multiplying any number by 0. Therefore, gates can fulfill both purposes by involving the sigmoid activation function. Question 3.3. Discuss the similarities and differences between the cell state in LSTM cells and the hidden state in the simple RNN cell. Similarities. Cell state aligned with hidden state make the memory of the LSTM neural network. Likewise, hidden state is the memory of the simple RNN. Both cell state and hidden state can carry information throughout the processing of the sequence and transfer information from the earlier to the later cells. Differences. The hidden state in simple RNN represents only short-term memory and can remember the information very close to the present, while cell states represent the long-term memory in the LSTM cell. In fact, LSTM has both long-term and short-term memories, which is very similar to humans' brain system. Therefore, simple RNN suffers from short-term memory effects, including vanishing and exploding gradient problems, while cell state can mitigate the problem of short-term memory in LSTM neural network. Cell state does not involve any weight, and hence information can move as it is through multiple layers if the information is relevant. In fact, any later time step can use information carried in from the previous cell state without any reduction. However, if the information is removed in a cell state at a time step, that information would be no longer moved to the next cell state at the later time step. Even though the information can be dropped at a cell state in a time step, such information is always reserved. Cell state is considered as an information transporting channel that can transfer the information from the earliest time steps all the way to the end of the sequence chain, while the hidden state involves wait. Hence, before the information gets into the cell from the previous cell state, it is multiplied by a wait. That is the reason why the output of the hidden state does not reveal everything within the hidden state. The hidden state is not a straight line, while the cell state is a straight line. Hidden state does not expose the structure of the information at each state of the simple RNN, while cell state, as the component of LSTM neural network, provides us the information about the state of the cell at each time step. Part 4, RNN LSTM with time series data. In this part, I have built, trained, and tested an LSTM neural network by Amazon stock dataset with CRUST. First, I imported Python libraries. I used a time series dataset that contains 1,200 stock prices of Amazon from January 2014 to October 2018 to train and test the model. The dataset contains open, high, low close, adjusted close, and volume columns. I kept only close column and filter out all other attributes. I specified 60 closing prices as the length of the input sequence. Then I split the dataset into two parts, 85% as training and 15% as test. 1,020 data points used as training and 180 data points as test data. Training data points have indices from 0 to 1019, and testing data points have indices from 960 to 1199. I normalized the data. I specified the length of the input sequence as 60, which is the number of data points that are used to predict the future one. As can be seen in this figure, I specified the batch size as a 32. By doing this, the time series generator creates 30 batches that each consists of 32 samples with 60 data points in each sample. As you can see here, I built an LSTM neural network by adding 6 layers to the sequential model. 3 LSTMs, 2 dropouts, and 1 dense layer. I assigned 100 neurons for all LSTM layers. I employed ReLU as an activation function and dense layer with only 1 neuron. I introduced MSE as the cost function and ADEM as an optimizer. Then the sequential model is trained by introducing 2 parameters, the batches of the input sequence and epochs. I specified 100 for epochs. It means that I trained the model in 100 alterations, and each alteration consists of 30 batches. The cost or loss function graph drops quickly at the initial steps of the training, which implies that the model has been trained very well and improved significantly. I evaluated the model. How will the model train? By predicting the test data. I assigned the batch size one input sequence. The last 60 data points of the training data set considered as the first input to predict the first value in the test data set. I dropped the first data point of the previous input sequence and appended the newly predicted value to the input sequence. By that way, I made a new batch to be used for the next iteration of testing. This process has been conducted 180 times as the number of testing values that led to generate 180 predicted values. To evaluate the performance of the trained model, I visualized the predictions and compared with the actual closing prices. As can be seen here, orange line that shows the predicted values is pretty close to the blue line that shows the actual values. Hence, the trained model did a pretty good job when it predicted. Next, I used the trained model to forecast the closing prices of 79 business days. Integrating the forecasted closing prices in this figure, orange curve, and the actual future closing prices, blue curve, reveals that the trained model could accurately forecast the unknown prices. Part 5, redesign the neural network. I redesigned the neural network built in part 4 to achieve a network with better performance by changing some parameters as explained here. Since the objective was to improve the performance of the previous network, I did not change the testing and training data. Therefore, the percentage of data for testing was considered as 15% throughout the redesigning process. I increased the number of LSTM layers and the number of neurons associated with each LSTM layer to examine the ultimate performance of the network. Another layer of the design neural network was dropout. Since each dropout drops a specified portion of the biases in the data that theoretically cause the network to learn better, I added one more dropout layer and increased the percentage of drop and examined how these changes affect the performance of the ultimate network. With respect to the median slope of the graph of data points, 60 data points seem quiet enough to predict the network. Thus, I decided to keep the input sequence as it was. I also changed the batch size to see how it affects the learning process. Additionally, I increased the epochs to provide more time to the neural network to learn and examine its influence on its performance as well. As you could see here, I changed the batch size into 48 and kept the other parameters as it was. As you could see here, the model performance is very well. The prediction for the testing is not acceptable, and the forecasting for future is good. I changed the batch size into 30. As you could see here, the model performance, prediction for testing, and forecasting for futures, all of them are quite acceptable. I changed the batch size into 30, increased epochs into 150, model performance and prediction for testing are acceptable, while forecasting for future is not acceptable at all. Then I changed batch size to 30 and I increased neurons into 120. As you could see here, the model performance is very good, prediction for testing is very good, but the forecasting for future is not acceptable. I increased the drop into 30% and batch size into 30. Model performance is very good, prediction for testing is good, but forecasting for future is not acceptable. I increased the number of LSTM layers and dropout layer into 4 and 3 respectively, and batch size into 30. As you could see here, the model performance, prediction for testing, and forecasting for future are not acceptable at all. Part 6, compare network performance. In part 4, I have designed an LSTM neural network with the parameters shown here. Corresponding to its loss function, the design model has been trained very well and improved significantly over time. The prediction graph shows the predicted values in orange and the actual values in blue. The predicted graph seems quite close to the actual graph, which implies that the trained model could predict the test values accurately. I could also conclude that the trained model forecasted the unknown future values pretty well, since the forecasted values in orange shows the same trend with the actual future values in blue. Among 6 redesigned LSTM neural networks, I have shown the best and worst model in terms of performance here. The parameters of the best redesigned model differ from model in part 4 only in the number of batch size, 30 samples rather than 32. As can be seen here, the model's performance increased rapidly in the earliest time. Furthermore, prediction of test data seems quite similar to the prediction of model of part 4. However, the redesigned model has shown a significant improvement in forecasting the unknown future values compared to the model of part 4. The worst redesigned model is shown here. This model differs from the model designed in part 4 in terms of number of LSTM and dropout layers and batch size. Even though I thought that by adding one more LSTM layer, transferring and managing information would be enhanced, and by adding one more dropout layer, the bias within data would be decreased, and then this redesigned model would learn better, I experienced the opposite effect. As can be seen here, the redesigned model containing 4 LSTM layers, 3 dropout layers, and 30 batch size shows a very poor loss function. Therefore, I can infer that this redesigned model has not improved at all during the learning process. In addition, this non-well-trained model could neither predict the testing values nor forecast the future values. Therefore, I could conclude that this redesigned model has not experienced any improvement. It seems that designing a successful neural network is a more complicated task that I have ever thought. In this project, I have learned how machine learns to think like a human when dealing with time series datasets. In part 2, I generated a sine wave dataset as a well-known time series dataset. I divided the sine wave dataset into training and test. Then I built, trained, and evaluated a simple RNN, which has only one single layer neural network. In part 3, I learned the core concepts of the LSTM neural network, including cell state and gates. I also learned that cell state can transfer information from the previous cells without any reduction if the information is irrelevant. In addition, cell state can regulate the flow of information using gates, unlike simple RNN that has both long and short-term memories and can mitigate both both problems. This is the main reason that LSTM neural networks have been widely used in real applications. In part 4, I collected a publicly available time series dataset. I split the dataset into training and test. I generated time series from the training dataset as training. I learned how to build, train, and evaluate an LSTM neural network. Then I used the LSTM neural network to forecast the future values, and I evaluated its forecast. Furthermore, in part 5, I learned that any minor change in one of the parameters of an LSTM neural network has a significant effect on the performance of the output network. In part 5, I redesigned 6 different LSTM neural networks by changing some parameters. I evaluated the performance of each redesigned network. Finally, I compared the best and the worst LSTM neural networks redesigned in part 5 with the LSTM neural network designed in part 4. To sum, I have understood how a well-designed recurrent neural network could successfully analyze time series data, and how designing of such networks is a difficult task and depends on different parameters. Thank you for your time.